Greetings of the day. Welcome back to the series on control systems engineering. In the first lecture, we saw the significance of a system, the system as we see in our daily life, and we covered a couple of examples of the same. In this lecture, we'll observe how the systems are modeled and why exactly we need the model of the system at the first place. This particular lecture will cover the significance of modeling of some sort of physical systems. There are numerous physical systems for that matter, but we'll be covering those which are important in the aspect of engineering, proceeding which we'll observe the analogy, the similarity in a couple of those systems. Now, to begin with, what exactly is a model? We have given certain examples of systems in the previous lecture. We have seen the driving mechanism, the lighting mechanism. We have discussed on AC ventilation systems. Now, if you consider any physical system present in and around us, a model, it can be referred as an elemental representation or the representation of the system in the most basic form, which captures the dynamics of the system. Now, here the term dynamics uh, is quite logical here. If we design a system and the parameters of the system changes, as in the variables of the system changes, that must be captured by the model in a proper or an efficient manner. Then alone it would be said to be a good model. The same model, if it is done in a proper fashion, wherein it is capturing all the dynamics of the system, we can use the same for analysis of the system. Now imagine here, we have a system which looks, say, a lighting based mechanism, wherein a person, I've just kept an observer for an illustration here, is observing the system as he supplies the system, electrical energy, of course, and the bulb converts that into a light energy. Now, the same system can be modeled as you see here by using Ohm's law, the basics of the laws. Current is equal to potential difference by the resistance of this light bulb. Now, while defining a model, an user or the designer has to take care whether all the dynamics required for depicting the model is being covered or not. Now, for this particular case, the model that we have given here is describing the resistive nature of the load, that is the light here. But it is not discussing on the intensity of the light or the heat. If you are supposed to design a system for depicting the intensity of the light or heat, the model would be different. So to sum up, a model for any system is such that it will definitely cover the dynamics of the system wherein there is a change, and these dynamics are user defined, or basically it is what you are expected to obtain from the system. Now, considering physical systems, these are those which you see around you. Now, the systems that we see around us, it has many classifications. Some of them I have enlisted here: electrical systems, there may be mechanical systems, pneumatic systems, which works with pressurized air, thermal systems, hydraulic systems, and electronic systems. These are some of the classifications. Now, all of these physical systems, they have certain elemental components or the basic components which working together forms an entire system. In the context of this particular course, we will be covering up electrical and the mechanical systems. And it is worth noting, if you are well versed with any of these mechanical or electrical, any of these physical systems, you can convert the given system into an equivalent electrical or a mechanical system, or so on and so forth. If you are well versed with any one of those, you can obtain an equivalent conversion from the given system, and you can analyze it in your own terms, and the results will be same. Now, in electrical system, we are much aware of it in this duration, in this period of your course, but still have a look. An electrical system, it is basically an interconnection of electrical devices or electrical components which controls the transformation of electrical energy, or say the transfer of electrical energy. Now, an electrical system can be divided in terms of the excitation to which it is subjected to. And the basic excitations are a current source and a voltage source. Now, if you consider an electrical system irrespective of the excitation, it will have three elemental components, namely the resistor, an inductor, or a capacitor. Now, irrespective of whether it is a current source system or whether it is a voltage source system, these three elements will be found in common. Now, the variables of the system depends on the nature of the source or the excitation. This we'll have a look later on when I'm explaining one of these systems, and then we can correlate how different variables are defined in if it is a current source system or a voltage source system. Now, we are aware of the basic elements of electrical system. Now, say for instance, if I speak about resistor, it is the element which opposes the flow of electric current. It is similar to friction in terms of motion. I'm keeping this as a point because we'll be needing this for future slides. And if we observe an inductor or a capacitor, these are those elements which have a tendency to store energy. An inductor will store energy in form of magnetic field, and a capacitor will store energy in form of an electric field, which you have learned already from your elementary classes. Let's have another basic, the Kirchhoff's law, the KCL, the KVL, the Kirchhoff current law. It is just a reminder. The algebraic sum of currents meeting at a node is equal to 0, and the voltage law, sum of all the voltages or voltage changes in a loop is always equal to 0. I'm placing this as a prerequisite for what we are going to see next. Let's have a look. Nodal analysis. Now here we have a circuit, we have a parallel RLC combination. It is supplied by a current source here. That's what we observe. Now let's name this node here. Let's name it A. Now we know, let's mention the currents here as say IR, here as say IL, and through the capacitor IC. Now we know from the KCL that the algebraic sum of currents which will meet at this particular node will be equal to 0. Now what do we mean by that? So the only incoming current here is this current from the source. So I can write it down as the current I will be equal to the sum of current through the resistor, the inductor, and the capacitor. Now I can go ahead and write down, assuming the voltage at this node A to be V. I can write down the current through the resistance to be V over R. The current through the inductor to be 1 over L integral V dt, and the current through the capacitor to be C dV over dt. Now we also know that the voltage, it depends on the rate of change of flux over a unit time. We are aware of this. Now if I substitute this rate of change of flux to the equation 1, the earlier equation, what we'll get? Let's have a look. I, it must be equal to 1 over R d phi over dt plus 1 over L phi plus C d squared phi by dt squared. Let's make a note of this particular equation, as we'll need this for further understanding. The moment we see a parallel network supplied by the current source, we define a node wherein some current is entering and some currents are leaving. And the currents meeting at this particular node will be zero. That's what makes us say I will be equal to IR plus IL plus IC. And IR is given by Ohm's law here through the basic formula for inductor, the current through the inductor. We can mention 1 over L times integral of V dt. And the current through the capacitor would be C dV by dt. The voltage is defined here as the rate of change of flux, wherein phi is flux here. Term phi is defined for flux. Let's go ahead and see mesh analysis. This makes use of the Kirchhoff voltage law. In any closed loop, the voltage changes or the sum of the voltage changes would be zero. Now observe this particular circuitry over here. And we have a voltage source supplying a series combination of R, L, and C. Assuming a current I, let's apply Kirchhoff voltage law. The supplied voltage must be equal to the voltage drop across the resistor plus across the inductor added with the voltage drop across the capacitor. Now we know the voltage drop across the resistor can be given as I times R. Across the inductor can be given as L di over dt. Across the capacitor can be given as 1 by C integral I dt. Now this we have a relation that we need to observe over here. If you remember in the previous case, the nodal analysis, there the current was taken as input and the sum of currents through the resistor, the inductor, and the capacitor were made to be equal to what was supplied. And in this particular case, the mesh analysis, we are taking voltage as the input, and we are saying the sum of voltage drops across the resistive element, the inductive element, and the capacitive element. These are equal to what actually we have supplied as the source, the voltage. We'll have a look onto this further in comparison with the mechanical system. That will give the real essence of control systems engineering. Now the mechanical system. The mechanical system can be linear or rotary. So it's basically broadly classified into translational and rotational system. Now, a system with a linear motion is referred as a translational system. Linear, as in which if you apply a force, the system would be moving linearly. And a system which bears a fixed axis, and if you apply the force, the system follows that axis. Then you'll name it as a rotational system. So it can be of two types, translational or rotational. Now, as we discussed the electrical systems, there are basic elements for mechanical systems as well. Now, the basic elements of mechanical system, we can have mass, inertia, damper, or a spring. Imagine an object in front of you. Imagine a box in front of you, and you are trying to push the box. You are applying a force in one direction, and the box will tend to oppose it by the virtue of its mass. It's quite intuitive. If you increase the mass, the force exerted by the object, or the force required by you to push the object, will increase. If you have a bigger object, it will be tougher for you to push it. If you have a smaller object, it will be easier for you to push it. Now, mass is the property of an element in a mechanical system due to which it stores the kinetic energy in a linear system or a translational system, wherein the force and the displacement are in linear motion or a translational motion. The same logic applies to a rotational system when we discuss about inertia. Now, if you observe a system which is fixed about an axis and you apply some force to it, or rather say a torque is applied, a force which has a rotary moment. If you apply torque to an object which is fixed about an axis, you'll experience an opposition, or rather say, consider a drum. Consider a drum which is empty, a cylindrical drum which is empty, and you are trying to roll it. Imagine that the force that you needed here to be of some magnitude x. The next moment, what you do, you just fill in the tank with some fluid. And now you apply force, expecting the same displacement. This time the displacement is angular. It's not linear because the object, it's a drum. By the shape, you could say, if it is fixed about an axis, the rotation would be, or the motion would be angular rather than being linear. This mass and inertia are quite analogous. For a rotational system, if the inertia is high, that means the system is heavy. And this too stores kinetic energy, and you would require more force, or say more torque, to turn an object with higher inertia when compared to one with a lower inertia. The next element, damper. We are all aware of damping mechanism, maybe in terms of friction. Suppose you are walking down the lane. If you are walking, consider two cases. You may either walk or you may either run. Which of these cases will give you a more opposition in terms of friction? The case where you are running, because your velocity is higher. Let's assume we have a bucket which is full of water. or say half filled. It's half filled. And try placing your hand into the bucket and try moving it. You will experience an opposition by the fluid. Imagine two cases now. In the first case, you are waving your hands slowly. In the second case, you are waving your hands faster. Go try this at home, and you would observe motion would be possible in both the cases, because the amount of force that we exert will of course be higher than what is being opposed by the density of water. But you would notice, if you are trying to wave your hands slowly, the opposition by the fluid will be weaker. Whereas, if you are trying to wave your hands faster, the opposition would be more when compared to the slower case. The term damper in a mechanical system, irrespective of linear or rotational, is observed to be the friction or the opposition in motion. The next term, spring. We are all aware of spring. We have played with springs as a child. And you notice, if you take a spring, it is basically an element which can store potential energy. If you stretch a spring by say some length, if you stretch a spring by some length, you'll expect the spring to return back to its initial condition, to its initial position or shape. Suppose you take a spring, you compress it to say some length, and you keep it as it is, keep it held. If you are able to keep it in the same position for say some duration, and then you release it, the moment you release it, the spring will return back the energy or the same force which you have applied already to compress it. So we refer a spring as an element which stores potential energy either in linear system or in translational system. So of all these elements, mass, inertia, damper, spring, we have to note a single point, and that is the elements mass and spring are those which can store energy, whereas the damper is an element which dissipates energy. If you keep this in mind, it will be really easy to obtain an analogous system later. Now, consider the first element of mechanical system. Here I have separated the page in translational and rotational system. However, just have a look. Suppose we have, let's observe a translation system first. Suppose we have a block, an object which has, say, certain mass m. And consider that there is no friction. No friction. Suppose it is placed at a surface and there is no friction between the object, the mass, and the surface. And if we apply a force, say in this direction towards the right, we'll expect a displacement in the same direction. And by Newton's second law of motion, you would say the force which is applied here, it would be equal to mass times acceleration, wherein x is the displacement dx over dt would be velocity, and d square x by dt squared, or d2x by dt2, would be acceleration. Now this equation, the above equation, it becomes m d squared x by dt squared. From here it is quite clear that the mass m is proportional to the force. That means if the mass of the system is increased, to obtain the same acceleration, you need more force. And the converse is also true. If you reduce the mass of system to obtain the same magnitude of acceleration, you need a lesser force. Now for a rotational system, here I'm saying that this is the axis. This is the axis about which this cylinder is attached. And I'm saying that I'm applying a torque, say in clockwise direction. I'm expecting an angular displacement theta in the same direction, and assuming the inertia of the system to be j. And at this instant as well, for this example as well, we are assuming that there is no friction. So here the torque will be given by this relation. Now you would observe from this particular example that force is analogous to torque and mass is analogous to inertia, wherein force and mass are the components of a linear or a translational system, and torque and inertia are the components of a rotational system. The electrical engineers who are watching this video, they must note down this can be a rotating part of your electrical devices, say motors, or the rotating part of your generator, which they make a good use in understanding electrical machines. The takeaway from this particular slide is a translation system and a rotational system, or both the mechanical systems, are analogous to each other in terms of mass, in terms of inertia. The thing that you have to notice is the linear displacement x is similar to the angular displacement theta. Force is similar to torque, mass is similar to inertia. Now the next element, the damper. It's a frictional element, as we have discussed already. And now with intuition, we know if the density of the fluid which is present in the bucket that I gave you an example earlier, if it is higher, it will give more opposition. And that opposition is not to the motion, but to the first order differential of displacement, that is velocity. If you are moving your hands quicker in the bucket of fluid, the opposition would be higher when compared to a case wherein you're moving your hands slowly. Now we would say the force which is required here in a translational system, this would be proportional to the density of the fluid, and it would also be proportional to the velocity. The combined equation can be given as the same is valid for a rotational system, wherein I'm expecting, see here for the translational system, the motion was linear. The force was exerted in a direction, say towards right, and we are expecting a motion in the same direction. For a rotational system, I'm giving a torque in, say clockwise direction, I'm expecting an angular displacement in the same direction. Now here, the torque would be given as, say let's take some other term for this damping. Maybe we can take the letter d times d theta over dt. Now from this understanding, it's also clear that force is again similar to torque. The translational damping is similar to the rotational damping. The linear displacement is similar to the angular displacement. And the linear velocity is similar to the angular velocity. Let's move to the next element, and that is spring. Now by Hooke's law, we know we take a spring and we compress it. The, the energy which is stored in the spring will be proportional to the magnitude of displacement. And the force that you require to compress or say elongate a spring depends on the tension of the spring. And that is referred as the spring coefficient. Now say for instance, we have a translational system here, and I'm trying to exert, assuming one segment to be fixed, I'm trying to exert a force on a spring, say towards the right, and it is getting displaced towards the right. The force here will be proportional to the tension of the spring and will also be proportional to the displacement. Now the equivalent force can be given as K times X. Now for a rotational system, this is a torsional spring. Here, let's assume the inner segment is fixed and the outer segment, if we move the outer segment, we displace the outer segment, and considering that displacement to be theta, depending on the tension of this particular spring, the torque will be given by K times theta. Here these terms, K, these are the coefficients. Now for the previous slides, for mass, M is the coefficient. For inertia, J is the coefficient. For damper, for translational system, B is the damping coefficient. For rotational system, D is the damping coefficient. And for a spring, in the translational system, it is generally represented by K in both the systems. So these are the coefficients that you have to observe. Similarly, here as well, force will be similar to torque. The coefficients would be similar. The angular displacement and the linear displacements, they would be similar. Now, all the three elements, that is the mass, spring, and damper, has been studied here. It is very important to note that while explaining the mass system, we are not considering the effects of friction or damper. Similarly, while explaining the damping mechanism, we are not considering mass or friction. Also, while explaining the spring mechanism, we are not considering mass and damping mechanism. These are the elemental study that we have done so far. Let's have a look onto a mass spring and damper system. It's a combined system. If you observe the system over here, suppose there is a wall, and we call this as reference, to which a spring is attached and a damper is attached. To the other end of the spring and the damper, we have a mass. All these things, all these mass, spring, and damping elements, these are elemental. Now, if you observe the force here, the force is given in such a way that the entire system of mass is displaced towards the right side. Now let's have a look onto it. Let's observe how we analyze this particular system. For analyzing a system which has mass, spring, and damper, we need to get free body diagram. And this free body diagram, it is obtained for all the masses which are present in the system. For this particular system, we have a single mass and the coefficient is m. We have a force which is applied towards right. Now we know, because of the virtue of mass, it will have a tendency to oppose the force. So we can expect an opposite force by the virtue of mass with respect to the acceleration. The mass is attached to the spring, and the spring-based system, since it is attached to the mass, it also is getting displaced by x. So suppose you have a spring here and you are stretching the spring by x units. You'll expect the spring to return back to its original shape by displaying or by exhibiting an opposition force with same displacement. Now let's have a look. So since the force was given towards the right, we'll expect the spring to act opposite with respect to the displacement. Now similarly for the damper, this damper will oppose the change in displacement, or say the velocity. And since it is friction, as we have derived already, it is given by b dx over dt. Now it's a general convention. I'll draw a plane wherein, let's have a look. We'll mention this as, say, the force plane. And the forces which are acting towards the right, let's consider them positive. Towards the left, let's consider them negative. Towards upwards, let's take them as positive, and the downwards as negative. If you keep this convention in mind, it will be easier for solving any combination of mass, spring, and damper system. Now let's have a look what we have in this free body diagram. We have a force which is exerted towards the right, so that has a positive sign. We have a force by the virtue of mass which is acting towards the left, so we have a negated version of the same. Similarly, for damper and spring mechanism, both of these are acting towards the left. And by equilibrium, we know all the forces will sum up to 0. So the final force would be given as m d squared x by dt squared plus b dx by dt plus kx. This can also be written as m x double dot bx dot plus kx. Now this is a mass, spring, and damper system. If you noted down the similarity of translational and rotational mechanism, you would also know here that torque would be j times double differential of theta plus d times differential of theta plus k times theta. Now the first case is for a linear system, and the second case it's for a rotational or a torsional system. We have maintained the analogy here clearly. Force and torque are equivalent, mass and inertia are equivalent. A linear damper and a torsional damper, or say a rotational damper, are similar, and a linear spring and a torsional spring, they are similar. Based on the analogy, the equations would be similar to each other. Now let's have a look onto analogous systems. As we have already spoken, if you are well versed with any of the physical systems, and if you are given with a system which you haven't come across or if you aren't aware of, but if you can convert the given system into its basic elemental form, an equivalent representation can be obtained in the system which you are well versed with. Now, a mechanical system can be represented in terms of its equivalent electrical components. And this is done in two analogies: the force current analogy and the force voltage analogy. The same is valid for a rotation system as well, wherein the input or the excitation force will be replaced by torque, and we'll call it as torque voltage analogy or torque current analogy. Let's have a look. The first one, force voltage analogy. As we are discussing about force, it must be well understood that this is a linear or a translational system, and we are supposed to obtain its electrical equivalent in terms of voltage, wherein the excitation to the system is voltage. Have a look over here on the screen, and if you remember the equation which we derived out there, we got V equals IR plus LdI over dt plus 1 by C integral I dt. We know that current I is rate of change of charge over time. The final expression that we can obtain here is R dq over dt plus L d squared q by dt squared plus q by C. If we rearrange in terms of decreasing order of the differential, we obtain LD squared q by dt squared plus R dq by dt plus q by C. Now in the mechanical system, the mass spring and damper system which we just saw now, which was of this shape, and expecting the force to be in this direction, we had a displacement in the same direction, and the force was represented as m x double dot plus bx dot plus kx. Now if we relate both these systems, if you observe, the input here in mechanical system is force. In electrical system, we have voltage. The mass is represented in terms of inductor. The damper is represented in terms of resistor, and the spring is represented in terms of reciprocal of capacitance. So the first line defines excitation. The meaning is, if we observe a mechanical system or a mechanical combination of mass spring and damper, as you observe here, and if we convert this into an equivalent electrical analogy wherein voltage is the input, the behavior will be similar to a voltage sourced system of R, L, and a C in series. The excitation is force here, and the response is linear displacement. This is the response of the system. Now for the electrical system, instead of X, you would observe X is very nicely replaced here as charge. Now with this equivalent, once you are able to obtain the mechanical system, you can directly convert it into an electrical system and you can observe the response. This analogy is really important as the subject of control systems is multidisciplinary. Irrespective of the domain of the learner, he can solve or analyze any system given to him or her by knowing the correct conversion. Let's have a look onto the next one, the force current analogy. Now consider a mechanical system, the same system as we have done already, as we have seen earlier, same mass spring and damper system. Now if we are supposed to convert the force excited system, or say the translational system, into an equivalent electrical system wherein current is the input, then you'd have to utilize the parallel RLC system, which is supplied by a current source. You have to consider a node here with some voltage, and you're supposed to sum up the currents and equate it to the supplied current, and you'll obtain this particular equation, wherein I have considered the voltage V to be a rate of change of flux. Now in the mechanical system, so if it is needed, I can redraw it for you. It is the same mass spring and damper based system which we have done already, with some force and with some displacement. Now by comparing these two equations, we can see if the force was input in the translational system, an equivalent can be represented in terms of current for an electrical system, wherein the mass is represented as capacitance, the damper is represented as reciprocal of resistance, or rather we can use the term, we can say it's a resistor, so reciprocal of that can be a conductor. Yeah, that makes sense. Now, and the last element, the spring, it is similar to reciprocal of inductance. The excitation in the mechanical system is force, and that in electrical system is current. The response in mechanical system is displacement, and that in electrical system is flux. This is flux, and it is the response. Now see the usability. If you are well versed with any of these conversions, you can analyze any system given to you. The force current and the force voltage analogy. You have to notice, and it is quite important not to remember these as a law. However, it must be derived by you so that you get used to the system every time you find a need of conversion. The thing that you have to notice is, for force voltage analogy, you're supposed to use a series RLC network, and force current analogy, you're supposed to use a parallel RLC network, and that will do the trick for you. The next is torque voltage analogy. Now here, the behavior is similar. However, we are considering the rotational system now. Now in the rotational mechanism, the input is torque, and the response is an angular displacement, which is fixed about an axis. Considering this to be the system, if you rotate, it's fixed about this particular axis, the needle, the righted tip. Whereas a linear system, you keep the system stable on a surface and you start moving it. Let's have a look onto this. Let's apply some torque to an inertia, damper, and a spring-based rotational system. And here, this is how the dynamics would be defined, which we have derived already. Now to compare this torque-based system, or say the rotational system, to a voltage-based or equivalent voltage-based electrical system, then we are, once again, just to remind you, we are supposed to obtain a voltage supplied system which is in series to a series combination of R, L, and C. And now you can notice very well that the input here in the rotational system is torque, and the input in electrical system is voltage. The response in rotational system is angular displacement. The response in electrical system is charge. This is charge. The inertia is represented as inductor. The damper is represented as resistor. The spring is represented as reciprocal of capacitance. The combination or the analogy is similar to a force voltage analogy. Just notice what are the energy storing elements and what is the energy dissipating element. Let's go for the next one. Let's have a look onto torque current analogy. Here we are considering a rotational system, and since it is a rotational system, we'll be exciting it by a torque and we'll be expecting an angular displacement theta. And we're supposed to convert that into a respective electrical system in terms of current as the input. Now, for better understanding, since it is the last form of analogy, let's have a look onto how a rotational system actually looks like. Here for this particular case, inertia, damper, and a spring case. We'll consider a rotating mass which is fixed about an axis, and the walls on which the object is placed or the rotating body is placed, it's exhibiting certain friction, and this particular friction is represented in terms of damper D. And assume there is a spring attached, a torsional spring, and I'm willing to rotate this system in, say, clockwise direction. It will give, I'm expecting an angular displacement in clockwise direction, and this is how the dynamics would be explained, determined there, which we have seen already, which is quite analogous to a translational system as well. An equivalent electrical system is with a current input, current as the input, given to a parallel combination of R, L, and C, We'll consider a node here and obtain the respective equation. So here for the rotational system, we have torque as the input and we are expecting some angular displacement as the output or the response. We have energy storing element as inertia, spring, and dissipative element as the damper. For an equivalent current analogous system, electrical system, the input would be current, the displacement the response will be flux. Notice this to be flux. The inertia or the energy storage will be capacitance and reciprocal of inductance. The dissipative element or the frictional force will be reciprocal of resistance. With this analogy, one can convert a rotational system into an equivalent electrical system excited by current. Now, as a final note, we can observe for a mechanical system and an electrical system the equivalencies. Just have a look onto an electrical system. You would reckon that inductor and capacitor, these are the elements which can store energy, either in magnetic field or as an electric field. However, they're storing energy. And the resistor is the dissipative element. Now, in any analogy that you observe from mechanical to electrical, whether it be a translational system or a rotational system, the mass or inertia, spring in torsional spring or linear spring, these quantities will always be related to inductors and capacitors because these are the storage elements. And the damper, whether it be a linear damper or a rotational damper, will always be related to the resistor. Notice this observation here. The storage elements are always related to the storage elements, respective storage elements in electrical system, and the dissipative elements are related to the dissipative element in electrical system. To summarize, in this lecture, we have seen the significance of modeling, mentioning it to be an important segment that a control engineer has to undergo or has to obtain so that he can capture the dynamics of the system. We saw in both the mechanical or electrical system all the dynamics starting from the excitation to the response was captured correctly in the model that we have obtained, whether it be a mass spring damper system or inertia spring damper system or RLC system, both in series and parallel. We have had a discussion of electrical and mechanical system, and based on which we derived the analogous systems. Now, say for instance, if you are given with some complex arrangement of a couple of masses and some springs and dampers, if you are able to deduce the dynamics of the system properly in terms of its differential equations, you can obtain an equivalent electrical system and you can apply all the laws of electrics and the response will still be worthy. The response will still be similar to what a mechanical system would have exhibited. More on this in upcoming lecture. Thank you for being with us. Stay tuned for the next part. Thank you.